Imagine looking up at the night sky and knowing, really knowing, not just intellectually acknowledging that almost every star you can see almost certainly once had planets, and that on some of those planets, billions of years ago, something remarkable happened. Chemistry became biology, biology became complexity, complexity became life, and then it stopped. Not slowly, not gradually, not in the way that ecosystems decline over millennia, but suddenly, completely, finally, planets that were once alive, genuinely alive, with oceans and atmospheres, and the intricate molecular machinery of living things became silent, dead, empty of everything that had briefly made them extraordinary. This is not a fringe idea. This is not science fiction dressed up in academic language. This is a conclusion that a growing number of astrobiologists, planetary scientists, and astronomers are arriving at independently, from different directions, using different lines of evidence. The universe, they believe, may be littered with the ruins of biospheres, with worlds that were once what Earth is now and are now nothing. And the question that follows from that belief, the question that nobody wants to ask too loudly, is whether Earth is on the same trajectory. I want to walk through the evidence for this idea, the mechanisms that could produce it, and what it means for us right now, on this planet, at this moment in history. To understand why scientists are beginning to think the universe might be full of dead worlds, you need to understand something about the history of life on Earth that most people don't fully appreciate. Life on Earth is approximately 3.8 billion years old. For the first 3 billion of those years, roughly 80% of life's entire history on this planet, life was nothing more than single-celled microbes, bacteria, archaea. Simple prokaryotic cells with no nucleus, no complex internal structures, no multicellular organization of any kind. For 3 billion years, that was it. The most complex thing on Earth was something you could only see with a microscope. Then, approximately 600 million years ago, something changed. Complex multicellular life appeared. Animals evolved. And over the next 600 million years, life on Earth went from simple worms to dinosaurs to human beings capable of building telescopes and asking questions about the origin of the universe. The point is this: complex life, the kind of life that builds things, that thinks, that develops technology, requires very specific conditions, maintained over extraordinarily long timescales. And the universe is not a hospitable place. The first mechanism that could be filling the universe with dead worlds is one that we've seen evidence of right here, in our own solar system's history: bombardment. In the early solar system, the space between the planets was filled with debris, asteroids, comets, planetesimals, left over from the formation of the Sun and its planetary system. For the first several hundred million years of Earth's existence, this debris rained down on the planet continuously. The early Earth was, by any measure, uninhabitable. A world of magma oceans and constant impacts that would have vaporized any ocean and sterilized any surface. Then the bombardment slowed, the debris was swept up, the solar system settled, and life appeared remarkably quickly after conditions stabilized within a few 100 million years of the surface, cooling enough to support liquid water. But here's the thing: not every planetary system evolves the same way. Not every solar system has a Jupiter. Jupiter, our solar system's giant, sits in the outer solar system and acts as a gravitational shield, capturing or deflecting a significant fraction of the comets and asteroids that would otherwise be on trajectories to hit the inner planets. Without Jupiter, the bombardment of Earth would be far more frequent and far more severe. The periods of stability that allowed complex life to develop here might never have lasted long enough. Many planetary systems don't have a Jupiter equivalent. Many of the exoplanetary systems we've discovered have their giant planets in the wrong place, too close to their star, in unstable orbits, unable to provide the gravitational protection that our outer solar system provides. Planets in those systems might never experience the sustained stability that allowed Earth's biosphere to build the complexity it has today. Life might start, microbial ecosystems might develop, and then another impactor arrives, and everything resets, over and over again, until the window of opportunity closes. The second mechanism is one that scientists have been taking seriously for decades, but that Webb has brought into much sharper focus: stellar evolution. Every star changes over time. Our Sun, right now, is middle-aged, about 4.6 billion years old, roughly halfway through its main sequence lifetime. But it is not the same Sun it was when Earth formed. It is about 30% more luminous than it was 4.5 billion years ago, and it will continue to brighten over the coming billions of years. This matters enormously for habitability. A planet that sits in the habitable zone, the region around a star where liquid water can exist on the surface today, might not have been in the habitable zone a billion years ago, and might not be in the habitable zone a billion years from now. The habitable zone is not a fixed region. It moves outward over time as the star brightens. For Earth, we are currently sitting comfortably in the habitable zone, but models of the Sun's future suggest that in approximately 1 billion years, a long time by human standards, but a short time by geological and evolutionary standards, the increasing solar luminosity will begin to trigger a runaway greenhouse effect on Earth, evaporating the oceans and ending complex surface life. 1 billion years sounds like forever, but remember that complex animal life on Earth is only about 600 million years old. That means the total window for complex life on Earth, from the Cambrian explosion to the Sun's increasing luminosity, making the surface uninhabitable, is only about 1.5 to 2 billion years. That's the window, and we're more than a third of the way through it. Now apply this to other planetary systems. Stars that are more massive than our Sun evolve faster, much faster. A star, 50% more massive than the Sun, burns through its fuel in a fraction of the time, brightening and eventually expanding into a red giant on timescales of only a few billion years. Planets around such stars have dramatically narrower windows for the development of complex life. By the time evolution has produced anything more complex than microbial mats, the star's increasing luminosity may already be triggering the conditions that will end the biosphere. And stars less massive than our Sun present their own problems. Red dwarf stars, the most common type of star in the galaxy, making up about 70% of all stars, are long-lived, stable, and potentially able to support habitable planets for tens of billions of years. But they are also prone to powerful stellar flares that blast nearby planets with intense ultraviolet and X-ray radiation. Planets in the habitable zones of red dwarfs are typically tidally locked, one face permanently turned toward the star, the other in permanent darkness. The conditions for complex life on such planets are, at best, challenging. At worst, they are fatal. The third mechanism is the one that keeps some scientists awake at night, not because it's speculative, but because we have direct evidence of it happening. Mass extinction. Earth has experienced 5 major mass extinction events in its history. 5 times, the biosphere has been devastated, losing between 70 and 96% of all species in geologically brief intervals. The most famous, 66 million years ago, was triggered by an asteroid impact. The most severe, 252 million years ago, at the end of the Permian period, was triggered by massive volcanic activity that released enormous quantities of carbon dioxide and sulfur dioxide into the atmosphere, causing rapid warming, ocean acidification, and the collapse of marine ecosystems. Each of these events was survivable. Complex life rebounded. Evolution continued. The biosphere, though devastated, recovered over millions of years and eventually produced greater diversity and complexity than had existed before. But there is no guarantee that every mass extinction is survivable. There is no law of nature that says a large enough impact, a big enough volcanic event, a sufficiently severe runaway greenhouse effect must leave survivors. On other worlds, with different planetary characteristics, different plate tectonic activity, different atmospheric composition, different orbital parameters, the equivalent events might be unsurvivable. The extinction might be total. And without survivors, there is no recovery. Life doesn't get another chance. The world goes silent. The atmosphere slowly escapes into space or freezes onto the surface. The oceans evaporate or freeze. And a billion years later, from a distance of light years, the planet looks like any other dead rock. There might be fossils. There might be atmospheric signatures of the biosphere that once existed. There might even be ruins if the life had progressed far enough to build things, which on most worlds it probably never did. But the life itself is gone. Completely and permanently gone. This is what the Fermi Paradox, in its most updated form, is pointing toward. The Fermi Paradox is named after the physicist Enrico Fermi, who supposedly asked during a lunch conversation in 1950 a question that has haunted scientists ever since. If the universe is so vast and so old, and if stars and planets are so common, why haven't we heard from anyone? Where is everybody? The standard answer is civilizations destroy themselves. They're hiding. They're too far away. We haven't been looking long enough. Are all unsatisfying in different ways. But there's one answer that doesn't require any assumptions about alien psychology or civilization trajectories. Most worlds that ever hosted life are dead. Not because the civilizations that arose there destroyed themselves, but because complex life is extraordinarily rare and the windows of stability required to produce it are extraordinarily narrow. And the universe is extraordinarily good at closing those windows through impacts and stellar evolution and mass extinctions and runaway climate shifts. Under this view called the rare earth hypothesis, and its updated versions like the dead worlds hypothesis, the universe is not full of civilizations that failed to contact us. It is full of planets that produce life, but never produced the sustained stability, the right kind of star, the right kind of planetary system, the right sequence of evolutionary accidents, to ever get past the microbial stage. Or planets that did get further, that produced complex life, even intelligent life, and then lost it. Not through war, not through pollution. Through the simple, merciless operation of physics and geology and stellar dynamics on a universe that has no particular interest in keeping its experiments alive. So, where does Earth fit in this picture? The honest answer is that we don't know. Earth has been extraordinarily lucky in ways that we are only beginning to understand. We have the right kind of star, a G-type main sequence star, stable and long-lived, not too large, not too small. We have Jupiter acting as our gravitational shield. We have the Moon formed from a giant impact early in Earth's history, which stabilizes our axial tilt and prevents the wild climate swings that would occur if our rotational axis precessed chaotically. We have plate tectonics, which cycles carbon through the atmosphere and ocean and prevents both runaway greenhouse warming and runaway glaciation. We have a magnetic field generated by our liquid iron outer core that shields the surface from the solar wind. These are not small things. Each of them is genuinely important for the maintenance of a stable, habitable biosphere over geological timescales. And many of them, maybe most of them, are the result of specific circumstances in our solar system's formation and evolution that might be difficult to replicate elsewhere. But lucky as we have been, we are not exempt from the processes that have ended biospheres on other worlds. The sun is getting brighter, the frequency of large impactors has decreased, but never reached zero. The climate system is, in some respects, more fragile than it appears. And unlike the extinction events of the past, which were driven by purely natural processes, the current period in Earth's history includes something new. A species capable of altering the planet's atmosphere, ocean chemistry, and surface temperature at a rate that has no precedent in the geological record. We are not separate from the natural processes that have killed other worlds. We are part of them. I want to be careful about what I'm saying here and what I'm not saying. I am not saying that Earth is doomed on any human timescale. I am not saying that the extinction of humanity is imminent or inevitable. The processes I've described, increasing solar luminosity, large impact events, supervolcanism, operate on timescales of millions to billions of years, far beyond any human planning horizon. What I am saying is something more subtle and more important. The universe's apparent silence, the fact that in all our searching, we have found no convincing evidence of other technological civilizations, no signals, no artifacts, no obvious signs of life beyond our own biosphere, may not be telling us that we're alone. It may be telling us that what we have here is rare, that the conditions that allowed us to exist, to think, to build telescopes, and ask questions are not automatically reproduced across the cosmos. That the universe is far less alive than its size and age might lead us to expect. And if that's true, then what exists on Earth, the biosphere, the millions of species, the 4 billion year history of life, is not just important to us. It is, potentially, one of the most precious things in a very large and mostly empty universe. The dead worlds are out there, orbiting their stars in silence, carrying in their geology the record of what they once were. And Earth, for now, is something different. What we do with that, how seriously we take the responsibility of being alive in a universe that may have very little life in it, is perhaps the most important question we face, not as scientists, as a species.